Okay, could I have a show of hands? How many of you have been to the poster session already that is going on right now? The Lunar poster session. Great, excellent, good. Well, I know there are a lot of students over there that are very eager to talk to you about their posters, so please, if you haven't, stop by and say hello. It says they'll be going on till 6 o'clock tonight. I don't know. We'll see. And now I'd like to get started with the beginning of this final oral session that we have today. This is capping just a wonderful day of talks that we've had on lunar science. And our first talk today is given by Jim Head, Geological Evolution of the Moon, Recent Findings, New Perspectives, and Fundamental Questions from 50 Years of Solar System Exploration. Thank you, Jim, for this invited talk.
Thank you very much, Yvonne. This is a really exciting time in lunar and planetary exploration, and I want to try to share with you some of my perspectives on this to challenge you to think about the near future. There's lots of things going on, and we really need to be thinking in new ways about this new incredible data set that we have. If we think about things from the point of view of the terrestrial planets, for example, we have at least one spacecraft in orbit around all of the terrestrial planets as we speak today. That's pretty amazing if you think about it. And indeed, when we do look at that, we really are trying to understand the most fundamental aspects of the formation and evolution of planets in our own solar system. They're all interrelated in some way or another, and that's a challenge to figure out what are the themes and what are the distinctive aspects about each one of these bodies. So I'd like to try to convince you today that we've had a lunar renaissance, and the moon is a touchstone for solar system science and perspective, if you will. Yes, there we go. Of course, this perspective began quite a while ago when we first launched spacecraft to the moon in the early, some would refer to as the good old days. In fact, we had a huge number of spacecraft, 20 automated spacecraft alone in preparation for Apollo and, of course, all the Luna and Lunicod and other spacecraft. That was an incredible era of exploration, and indeed, there was a lull after that, of course, as we're all painfully aware of. We got a good picture of some comparative planetological aspects with the moon as a baseline. But indeed, there were a huge number of questions that were raised by Apollo and the data that were returned, and essentially a dry spell in here until this period of time when Prospector and other missions came back in. And this is indeed, over the last decade and into the next one, the renaissance, if you will, in lunar exploration. And let's see, I probably pushed the wrong button there. There we go. Let's try it again. So this is what the exploration looks like, if you will. For example, the Renaissance in this period in the next decade is really the rebirth, if you will. It started out with Smart 1 and Prospector, et cetera. China is launching missions as we speak. Japan, India, the United States, Russia, indeed, with some upcoming missions, and indeed even the X Prize people are going to the moon. And this is a statement that was purported to have been made by Albert Einstein at the advent of the nuclear age, in which he said, everything has changed but our way of thinking. And what I want to try to tell you today and convince you of is, in fact, so much has happened so fast that everything has changed but our way of thinking. And we need to engage this new way of thinking and really plan for the near future to take advantage of all this. I'd like to put this in the context of a touchstone. If we start out and think about what this Renaissance means, we could refer to it as a cornerstone in which all other stones will be set in reference to it. We don't want to do that because the moon has many unique aspects of its history. It could be a keystone, which is a central cohesive source of support and stability. Indeed, the moon is that, but I'd rather talk about it as a touchstone, which is a physical or intellectual measure by which the validity or merit of a concept can be tested. This is, I think, what the moon is all about, and it's huge in the context of what it can tell us about the other planetary bodies. This is a list that I have in the abstract. I won't go over this in detail. The point here is the golden age of solar system exploration and the lunar exploration and lunar historical paradigm has raised a whole new series of questions that we need to get about answering in the short term here. We need to think about what the thematic themes are, if you will, the thematic aspects of planetary evolution are, and what is unique to the moon and the other planetary bodies. So we have, for the moon, each one of these things, like accretionary history, impact cratering record, magma ocean-derived primary crust, differentiation, so on and so on. All of these things can be addressed in our exploration of the moon, and indeed it is a baseline and a touchstone for understanding the rest of the solar system. So let me just touch on a few of these to illustrate what I mean about the new data. So we know the moon formed from an impact of a Mars-sized object into early Earth. This is an ancient diagram which illustrates this concept, supposedly devolatilization, ejection, reaccretion, etc. And over the past course of just a couple of years, there have been huge advances in understanding here, okay? Not just from the samples that have been re-examined on the moon, like Alberto's work on the glasses on the moon, discovering water, Francis McCubbin's work, Laura Kerber's, Sharp, and others, and a great discussion we had at the NLSI Microsymposium last year on the new models for the accretion and reaccretion. And of course, what we heard from Robin Canup today with these incredible new concepts for the ratios and mixtures of two bodies that would lead to the formation of the moon. And I'll come back to this in a second because we have new data on, in fact, what the bulk composition of the moon might be. So this is all really amazing. The starting conditions are really getting to be understood in much better context, and we need to catch up with this in terms of our models of the moon. But this is a unique thing. The moon is unique in this way because other planetary bodies probably didn't start out this way, but we can get great lessons from this as well. The early moon was characterized by a global scale magma ocean. We adopt Ross Taylor's concept of heavily cratered surface and accretionary energy causing melting of the upper portion of the planetary body, and then essentially a plagioclase flotation crust, and then evolution subsequent to that, in contrast to the later secondary crust, and maybe even on the Earth, like tertiary crust made from primary and secondary crust. So we're learning from Mercury now that, in fact, flotation crusts aren't exactly what's going on, and what we see on Mercury is beginning to blur the distinction between primary and secondary crusts. And so this makes the moon an even better paradigm because of the flotation crust to really understand the processes that are operating in that early period of time. We also know, of course, that, in fact, there's a huge number of models that have come out over the years. And in fact, for what this lunar magma ocean would be, lower left-hand corner here, you can see models for incomplete melting, more complete melting, the whole structure predictions from petrology, models for the aftermath of the formation of the magma ocean and the overturn, etc., and understandings of the upper part of the crust from data from the seismometers and other aspects of examination of the moon in the Apollo era. On the other hand, when we take a look, we also have now a whole set of new data. I mean, like new data this week, okay, from GRAIL. So this is the paradigm, if you will, for the crust. Comes out of the New Views of the Moon book, about 50 kilometers thick, more or less organized like this, if you will. The new GRAIL data have shown us something very, very significantly different, okay? It is, in fact, that the fracture porosity may go down into the mantle, okay? The thickness of the crust is now much less than it was before, in the 40-kilometer range or less. And indeed, this has a huge influence on our thinking about the bulk composition and the amount of feldspar and plagioclase and other kinds of things that, that are telling us about the comparisons of the Earth and the Moon. And so all of these things are brand new and really represent fundamental new aspects to our thinking about the evolution of the Moon. Furthermore, we have huge amounts of information from the spectrometers. Read this book. This is just amazing. We have discovered new minerals. We've discovered new associations, and you heard Junichi Hiroyama this morning talk about the Kaiguya data. Just absolutely amazing, okay? So this is really something that we need to link to. We're just making discoveries that are unbelievable in terms of the associations, the locations, and how we would go about exploring these into the future. So the Moon initially differentiated into chemical layers, including crust and mantle, that set the stage for further evolution. And we now have access. You can see from all these maps, from different aspects of the literature, not too distant past, we can actually, you want to know what the mantle is? Here's a map of where to go to get it, okay? We can actually go and get pieces of the mantle based on these types of maps. Not only that, maybe there's even tertiary crust here. Tertiary crust on the Moon, the Grotthuysen domes here, they're just amazing, okay? They are essentially things that may in fact represent basal melting of the highland crust and incorporation and evolution of very viscous magmas, very distinctively different. And so, you know, if you wanted to land on one of these things, you could use a spectrometer as a homing device because they're so distinctive, literally, they're 20 kilometers wide, a kilometer high, 1,200 meters high. We can go get these samples and really test these hypotheses. And of course, we know that the Moon is stratified into mechanical layers, the lithosphere, the outer thermal boundary layer, and so on, and it thickened and became less heterogeneous with time. Many years ago, Sean Solomon and I showed that the near side and far side, based on flexural observations, were different. And in fact, when we were able to look at, as a function of time, we could see a thickening of the lithosphere and an averaging of the lithosphere out as a function of time as, in fact, the Moon cooled down. Well, there's a map here, okay, of these variations and these differences. And we didn't know at the time what they were due to, but in fact, we can take a look at other aspects, which is the flexural aspects. Think about the moon as a one-plate planet, which enables us to get at what's going on in terms of the thickening of the lithosphere and these fundamental variations. And when we do that, we find out that, in fact, in some of the areas where the lithosphere is thought to be thinnest earliest, correspond to the Procolarum creep terrain. So this is a really important aspect. We have great geochemical data that can get even better if we fly our instruments right, for the distribution of radioactive elements that are the most fundamental aspect of determining the thermal evolution of the planet. We heard a lot of talks this morning about this and how we link to heat flow, global heat flows. This is a map of where to go, okay, for heat flow experiments in the future, both on the near side and the far side. If we take a look again at the nature of secondary crustal formation, that is the partial melting of the mantle, we have a pretty good model for what's going on for the generation, ascent, and eruption from petrology and volcanology. But we also have a map here of the ages of these Mare basalts. This is pretty darn amazing when you think about it relative to other planetary bodies. This map by Hiesinger and his colleagues, in fact, show the distribution of these and excellent ages on these. We now have LROC data, so we can go back to the Apollo sites and calibrate these in excruciating detail and then re-extrapolate here. The answers aren't going to change that much, but it'll really make it more fundamental in terms of our understanding. And note, too, that we can go to this place right here where some of the youngest basalts are, and in fact, we find that's the middle of the Procolarum creep terrain. Coincidence? Probably not. But exactly how it happens is really kind of unclear. So there were some great ideas by Wazorik and Phillips early on, 2000, okay? And so these need to be tested, and we have the ability to do that with sample return and even more detailed data. We can also now date things on the far side and the limbs. So Jennifer Whitten has done dates on all the Mare basalts in Oriental Basin, and has shown, in fact, that the range of ages for these is exactly the same, shown in yellow here, as the distribution on the near side. It's just that the volumes are much smaller. This could be due to, in fact, crustal thickness variations, okay? So there's an idea that can be better tested, and compared to some of the discussions this morning we had about the nature of the depleted mantle layer overturn and the aftermath of that. Let me just point out here that the moon is a fundamental laboratory for the study of impact cratering processes, particularly at the complex crater to multi-ring basin scale. The data that we've gotten from LRO and other instruments has totally changed our thinking. We can go from static models of what's going on with impact cratering processes and use these new data to put constraints on what's going on. So let me just run through a few things here. We know, in fact, what the sequence of craters are from a morphological point of view, but we can now look at their distribution. Using the LRO LOLA data, we've mapped every crater on the surface of the moon greater than 20 kilometers in diameter, and in fact we can look at the density of these and go to the oldest places, the most heavily cratered places on the planet, to recover parts of the oldest crust that we can find on the moon. So these are kind of guidelines that we can use. We can also map out the distribution of all these different deposits, these different types of craters, and compare them to their onset diameters on Mercury and other places. And we can measure every bloody thing you'd ever want to measure about a crater, okay, which may sound silly, but when you do this, okay, what you can find from these data is the trends that go from complex craters through peak ring basins to the largest peak ring basin. And you see some significant variations, such as the change from the central peaks to peak ring basins here, that need to be explained in any of the models that we're producing to, in fact, hydrocode models, et cetera. So this is a roadmap for hydrocode models to use, if you will, to refine the kinds of input parameters that they use. This is really great stuff. And wait, there's more. GRAIL in orbit around the moon, the two spacecraft, are letting us look at the distribution of the gravity anomalies, particularly the positive Bouguer anomalies, as a function of increasing crater size. And this is like having a magnifying glass into the subsurface structure of these craters. We have beautifully preserved surface structure, beautifully documented with GRAIL subsurface structure. What more could you ask? Okay, it's sitting here right in front of us, so we have a much better understanding of cratering from these types of things. We can go look at these in other places too and look for variations in space and time with these as we look at the global aspects here. And then, of course, we can make measurements which let us look at these variations in these cratering parameters, which give us the modeling input to really refine these types of models. And then if we go look at the youngest basin, Oriental, this is one of my dreams for God knows how many years looking at this thing. We now know, for example, with the detailed topography, what the morphology and topography look like. We know what the geology looks like. We know what the gravity looks like. We can go here, look at the thickness of the ejecta measured from these altimetric measurements, the volume of impact melt. All these are inputs to the hydrocode models, which are going to make them, and they're improving too, they're going to make them even better than before. But wait, there's more. We can actually sample just a little bit more. We can actually look at these. Apollo 15 landed at the equivalent of the Cordillera Ring on the Apennine Mountains. We can actually link our existing sample collections to what we see, in fact, at the present time. So from these different types of remote sensing measurements. So the lunar sample collection is really alive and telling us that we need to go back and look at this in a lot more detail and really understand what's going on. We can look, in fact, at the populations using this new data set to understand what's going on in the early bombardment history of the moon. We can compare these onsets of volcanism and cratering to Mercury and things like that. We have magnetic data, okay? We can actually study the history of the magnetic field at the present time with the samples and with the measurements from orbit and learn something about the way in which the magnetism has changed and the history of the core, okay? The evolution of the core is totally linked to this as it is to the history of the orbit of the moon. So the last point is volatiles, and of course this is something that has been discovered with this new renaissance and has really profound influences, not just where the things are coming from. There are obviously, as we heard this morning, multiple origins from the mantle as well as from interplanetary space, and this conundrum and understanding of what's going on with this is a huge goal for exploration in the very near future. So all of these things really are changing our way of thinking. There's just so many different ways to look at this now. They're fundamental new questions, as illustrated here and in the abstract. And I would just say to you that what we need to do here is think of brand new types of robotic exploration, human robotic partnerships, because we know where to go. We know what to do. We know what the new questions are, and we really need to get on with it and figure out what's going on here. We have absolutely not been there and done that, okay? So I want to close with this one last slide. Just before the Lunar and Planetary Science Conference coming up in the very near future here in March, we'll have Microsymposium 54, which will in fact consider these aspects and talk about new exploration destinations on the far side of the moon and the poles. So I invite you all to come to that and help to push along, as we're doing with our Russian colleagues, exploration of the moon. Thank you very much.
Thanks very much, Jim. We have time for just one question. Are there any questions? No? Okay, well, thank you very much.
I'd just like to acknowledge the role of the NLSI in pulling all these things together, because if it wasn't for that, we would really be in trouble in terms of integrating all these types of things into views of the moon. Thank you.
Thanks. Our next speaker is Dr. Carly Peters, also of Brown University, who's going to be speaking on space weathering on airless bodies.
Okay, thank you. Well, we're going to change gears just a little bit. We're going to be talking about space weather, which involves the sun and everything in between it and the planets, but it's planet-wide, and in particular, all airless bodies are involved in this. Since I think most of you have not thought about space weathering, I thought I'd need to give a little bit of overview of what some of the concepts are, but we'll get very quickly into some of the details, and hopefully by the end you'll understand why we're all excited about pursuing this even further. First of all, basic space weathering, what is it? Space weathering refers to really an array of processes. It's not one process. It's quite a few. This is a cartoon that many of you have seen. For those of you who are familiar with it, I've actually modified it just a little, adding a few more things that we've learned in the last couple of years. So space weathering applies to a variety of surfaces, and in particular, they alter the surface with time based on their presence in the space environment. So that's very general, and we're going to look at some specific aspects of this over the next couple of minutes. Here's another overview of the inner solar system. The body on the right there, of course, is Vesta. All of these bodies are differentiated. So they really involve lots of the processes that Jim just has been discussing about. What this talk is about really only discusses those that are airless. And that's the airless bodies that are subjected to space weathering processes. I won't be talking about Mercury, although obviously a lot of the topics that I do mention are applicable to it. We just need a little bit more information. Of the airless bodies visited, these are all the airless bodies other than Mercury that we visited, all drawn to scale. You can see the moon, you can see Vesta, and all the array of asteroids that we visited. That little tiny one down at the bottom is 1 pixel, and the little line shows what it is. It's the smallest. It's about 500 meters in length. Now, what I'll be talking about and emphasizing, however, is those airless bodies we visited that we have ground truth for, because this is really important for us to understand the processes involved and really be able to validate them with some more fundamental understanding. So these are these 4 I've circled are the ones I'm going to be emphasizing this afternoon. Okay, first of all, the moon. The moon is where we first really learned and got our feet wet, so to speak, about space weathering. When you look at a nice ground-up rock, you see these beautiful diagnostic absorption bands due largely to pyroxene in this case. But when you look at soils that were derived from the rock, it's not just ground-up rock. It's been altered. And consequently, we started calling this space weathering. And for the moon, the principal aspects that we see is that in the visible part of the spectrum, the soils are darker. We see that these very diagnostic absorption bands have been weakened substantially, and we also see that there's an overall continuum slope to the soils, namely brighter at longer wavelengths. We call this the red slope. Now, since Apollo, there's a large array of literature that have tried to address different aspects of what this could be due to, and I've listed several of them here. Each one of them has countless publications associated with them. The ones listed at the bottom are what we've been learning over the last decade with the modern instrumentation, and which has helped us to really understand the details of what, in fact, is causing the space weathering as observed on the moon. And it has to do with the finest fraction of the soils, and in particular the development of what we're calling nanophase iron on the rims of individual grains. Now, I need to explain that concept further, and in particular contrast it to one of the last ones we looked at before we started investigating nanophase iron, namely a process called shock impact darkening, because this is going to end up being very key as we walk through the rest of the bodies that we look at. So these 2 concepts are summarized in 2 different examples here. On the left is an ordinary chondrite spectrum. Again, it has diagnostic features of pyroxene. It also has some olivine in it. But some of these materials are in the same meteorite are much darker. And for petrologists who've studied this, they call it either impact darkening or shock darkening. And you'll see that the characteristics of this darkened zone have microscopic, namely millimeter-size blebs of iron and troilite that's disseminated throughout the material. Let's walk through this a little bit in more detail. In particular, here's an example of one of these bright and dark meteorites that have light-colored zones that are nice crystalline. It's the part that has the strong absorptions. And then right next to it is this shock-darkened zone. When you look at a thin section of this at higher resolution, the bright class are transparent. The darker zones are very opaque. They're very messy. This is in transmitted light. If you look at that in reflected light, you see that this opaque area really are rich with these very fine-grained opaque components of iron and troilite that's finely disseminated due to the impact process. Same composition, just different form of the opaque component. Okay, so that's what's happened with ordinary chondrites. Now, on the moon, we have, as I just referred to, a similar situation, but we have this red slope. And the cause of this is 3 orders of magnitude smaller than what we have in the shock-darkened situation. And in particular, it involves the nanophase iron. So let's walk through some of this properties in a little bit more detail. Let's see, here we go. When you look at the finest fraction of the soil separated in laboratories, here's an array of highland soils down to basaltic soils, but the very, very finest fraction. And you'll see that especially for the basaltic soils, it looks very much like our space-weathered soils. Well, this is the finest fraction. If we do experiments and mimic the characteristics of this nanophase iron, this is some experiments that Sarah Noble did years ago, and mimics exactly what is seen in the finest fraction. That little bleb on top of it shows the scale of the nanophase iron. It's only, in this case, a few nanometers in scale. You can make these particles larger, and when they get larger, the red continuum starts diminishing, and you get a flat spectrum. So these are tied together with very closely as the particles get larger. Simultaneously, in Japan, some experiments were done using pulsed lasers to mimic micrometeorite impact, and the same sequence is seen, namely that you can alter the optical properties of minerals with this phenomenon. And when you look in detail at what's causing this, again, it's this nanophase iron. You can examine it in detail. Everything holds together beautifully. What we now understand, or those people who've been involved in this, is for the moon, we have this really nicely laid out situation where you've got deposits on grains of a different composition than the grain itself, and within these grain coatings are these nanophase irons. And in some cases, you can see there's layers of these nanophase iron. And because of the layering and the difference in composition, most people who've worked with lunar space weathering really think that the dominant process is more likely the impact vaporization and deposition as opposed to solar wind sputtering. But that doesn't say that solar wind sputtering doesn't exist. It's just that for some of the processes we see on the moon, it requires a different, the depositional component. Okay, that's the moon. This is what you see when you look at the moon remotely. You see, again, the same sort of thing. You look at a fresh crater, nice, bright, well-developed absorption bands. As you move out towards the soils, you see the space-weathered component. The absorptions get weaker, it gets darker, and you have this red slope continuum. This is well known, we all agree. Okay, let's now move on to other airless bodies. In particular, Eros. This was not... we don't have samples from Eros, but we do have a spacecraft that orbited Eros and then landed on Eros and did in situ measurements. So we know a lot about Eros, and in particular, prior to going to the body, we see the spectrum of Eros and the spectrum of ordinary chondrites. They have the same mineralogy exhibited. However, the Eros itself has a redder sloped continuum, and the thought was maybe it's lunar-like weathering. Well, to do that, we have to know, is this body really an ordinary chondrite? And I got to speed up. We landed. This is one of the last shots. They really got close. And lo and behold, when you do the chemical analyses, it's clear that Eros is an ordinary chondrite, or if it's not, it's something that really is masquerading very closely like an ordinary chondrite. Moving on, as you well know, the Hayabusa mission orbited Itokawa and obtained some soil grains, and this is important, soil grains, returned them to Earth. Itokawa itself shows modest amounts of this continuum slope that we've seen at Eros and other bodies. When it was, these grains were returned to the samples to be studied in the laboratories, two things became very apparent, namely that this body, Hayabusa, is in fact a ordinary chondrite. Not only that's an LL ordinary chondrite. There's no question about that whatsoever. And what's more important for space weathering, when you look at the individual grains, they have these nanophase coatings on them. Nanophase iron, but also sulfur bearing. So it's exactly the same sort of thing we saw at the moon, just less of them. Okay, so summary, moon, Eros Hayabusa, space weathering, as we understand it, optical alteration is controlled by this development of nanophase iron or on the surface. Both solar wind and micrometeorite could be the cause of this. The near-Earth asteroids exhibit significantly less of this form of space weathering than on the moon, and nanophase iron is the principal phase that is causing this. Well, now let's move on to Vesta. Because at Vesta, Vesta has these beautiful, highly diagnostic mineral absorption bands due largely to pyroxenes, and even before we got to Vesta, we could model it without any space weathering. So before we got to Vesta, we didn't need space weathering. Well, when we got there, we saw Vesta is very complex, and in fact, here's some beautiful craters, wonderful rays, and right next to it, the rays are gone. Vesta has some form of space weathering. You remove rays, you can't avoid that. So what's the situation with Vesta? Well, the long and the short of it is that, yes, Vesta has these absorption bands. You can have variations in the strength of these absorption bands relative to the brightness. However, you notice that there's no continuum slope. There's none of this red slope. So it doesn't look like the moon. We've got the variations band strength, but we do not have the continuum slope. Therefore, it cannot be the same form of space weathering that occurs on the moon. So here's our summary. Prominent absorption, prominent bright rays on Vesta occurs. There is space weathering there. There is a direct correlation between this absorption band strength and albedo, but no variation in the continuum slope, which says that although space weathering occurs, it's not the nanophase iron, has to be something else. Well, here's the two key questions then. What is the causing the space weathering on Vesta, and why isn't there nanophase iron? Well, this is why I went through the long, detailed discussion of these two kinds of effects of different particles. And it's a matter of scale. The small micron size will darken and weaken the absorptions. The nanophase iron gives us the kind of lunar type we have. We have similar situations on some of the HED meteorites, same sort of thing. It's the larger particles, not the nanoparticles. And here we are. Here's the answers. And the last concluding remarks, what I really want to get to is, I hope you see that there's differences in scale of space weathering, same variety of processes across the solar system, but now we really have to go back and understand which processes are acting on which part of the solar system. And this last bullet, if we want to understand the time scale of space weathering, we really have to work at all of these together. It's not one size fits all. Thank you.
Thank you. What a wonderful talk. And Carly, I just hate to do this to you. I'd love to ask questions, but I'm already several minutes into the next speaker's time. But that is absolutely fabulous. And it sounds like a good reason to have an institute that covers the moon and airless bodies. Okay, our next speaker is Andrew Poppy. And Andrew's going to talk to us about recent advances in understanding lunar surface charging, modeling, theory, and spacecraft observations. This is an invited talk. Thank you, Andrew.
All right, good afternoon. As Yvonne mentioned, I'll be talking about some very recent work that we've been doing from both modeling and theoretical standpoints and also from spacecraft observations to further our understanding of how airless bodies, specifically the moon, but also talk about a couple other examples, how airless bodies in space react to electrical currents around them and how they charge up. Very important to acknowledge my co-authors on this. At Berkeley, I have both Jasper Hollicus and Greg Delory. Bill Farrell at Goddard. We're part of the DREAM Institute as part of NLSI. But also my former advisor, Mihai Hirani at Colorado, and Vasilis Angelopoulos at UCLA. So this is an oft recycled plot, an oft used plot that in my mind represents the canonical picture of our understanding of lunar surface charging, in this case specifically in the solar wind. The sun really is the main driver in this case. You see it off to the left. On the day side of the surface, ultraviolet photoemission causes the surface to be dominated by photoelectrons. It's positively charged. On the night side, the lack of photoemission means that collection of ambient electrons from the solar wind really drives the surface negatively. So we have this nice dichotomy that on the day side the surface is charged positively, the night side the surface is charged negatively. There's a few indications of other things that may be occurring. There's perhaps some things going on at the terminators where light and dark shadows can play together, perhaps, but I'll address more, generate what we would call supercharging or very strong electric fields, much stronger than one might expect at the subsolar point. But what's really interesting about this picture is I believe that in the last few years, there's been a lot of subtleties that have been revealed that aren't really represented in this picture at all. And that's what I'm here to talk about today. Now, some of the beginning observations that we have of the electrical interaction with the surface of the moon. The first one comes from the Charged Particle Lunar Environment Experiment, or CPLE. It was deployed by the Apollo 14 astronauts, and it was an electron detector that faced upwards from the lunar surface. It was able to measure electrons that ran from about 40 electron volts up into the kilo electron volt range. Turns out that the lower limit of this 40 electron volts is somewhat high compared to what we expect energies for photoelectrons being emitted from the dayside surface. So CPLE really only provided the hints of really verifying that these photoelectrons were dominating the dayside. Nevertheless, it really did show the right effects, the clearest of which is there was a pass through an eclipse. You saw all the electron counts disappear. As soon as the sun came back out, the electron counts appeared. So CPLE really provided the first realistic ground test. Later in the 90s, we had the Lunar Prospector mission. This, in addition to a couple of other instruments, contained a magnetometer and an electron instrument. And that allowed us to perform what's known as electron reflectometry, where we watch electrons go down towards the surface. They interact with the moon electrically, either through electrostatics or magnetic fields. They're modified somehow in energy or in angle. They come back up to the spacecraft. And by comparing the downwards and upwards fluxes, we're able to actually infer not only the crustal magnetic field strength at the moon, but also able to back out what the lunar surface potential and what the lunar surface charge is. There's a wealth of papers, mostly by Jasper Holocaust, listed here at the bottom, that really delve into day-side, night-side charging, a lot of very interesting effects that really have helped to show the picture that I showed before. Following Lunar Prospector, there's been in the last few years some new modeling and some new ARTEMIS observations that have really begun to add another layer of complexity to this. The first that I'll talk about is a series of one-dimensional simulations that I performed over the past couple years that looked at if you put a solid surface, aka the moon, on this side of the plot, and you allowed electrons and ions from either the solar wind or in the terrestrial plasma sheet in the magnetotail to self-consistently interact and charge with the lunar surface, what types of electric potentials do you get out? Now, straightforward charging theory would just simply tell you that you would charge slightly positive in both cases and slowly but surely die off to infinity. However, that's not what the simulations showed. They show these complex features where we see what are called non-monotonic potentials, where for part of the potential, the curve is going downwards. At some point, it hits an inflection point, a minimum, and returns upward. And this is caused by a balance of these photoelectrons that are dominating here near the lunar surface, both in the solar wind and in the terrestrial plasma sheet, versus the interaction of the incoming electrons, whether that be from the solar wind or the terrestrial plasma sheet. And it turns out that in these simulations, these were the equilibrium solutions. These lasted long past any time scale in the problem. And that suggested to us that these may actually be the dominant type of charging on the lunar surface. And we used both of these simulations to go ahead and to look at the spacecraft data to see if this type of charging, contrary to what one would typically expect, is what was actually at the moon. Now, one of the more recent ways in which we've done this is by using the dual-probe ARTEMIS mission. It's two satellites. They're orbiting in the moon in elliptical orbits. They go anywhere from very close to the surface down to tens of kilometers, all the way out to 10 to 12 lunar radii, so we get a nice long span of everything in between at the lunar interaction region. It's everything a plasma physicist would want. It's low and high energy electrons, magnetic field and electric fields, electromagnetic waves, and they really have allowed us to dig in to what this lunar surface charging is looking like. I'll show one observation that we have. This is from about a year and a half ago, July 16th, 2011. And these two time panels up on the top, you're seeing as a function of time, ARTEMIS, one of the ARTEMIS probes, swung by the front of the moon, and these whiskers are showing the magnetic field lines that are connecting down towards the surface. And this allows us to use this electron reflectometry method of watching how ambient electrons are modified by the lunar surface. Now, this middle plot shows the electron energy spectra as a function of time. It's fairly isotropic. It's nice and quiet. This is what's coming down towards the lunar surface. However, when we look at what's coming back up from the surface, it's highly modified. You see high energy fluxes are gone. In the black color means there's absolutely no counts. Those are electrons that have made it all the way down to the surface and been absorbed. However, you see two features of note. There's some of these electrons that have been reflected from the day side of the lunar surface. And there's this very curious feature, this very narrow and energetic, the bright red beam that's coming up from the surface. Now, the explanation behind this beam lies in these potential contours. The lunar surface being here, as it's photoemitting, it develops this self-consistent non-monotonic potential. Most of these photoelectrons are trapped here near the surface, but this thin arrow here is denoting that the very tail end of that distribution of electrons is leaking out and subsequently being accelerated up and towards the spacecraft. And that provides for us a wonderful measure of what that potential is, because the energies of these photoelectrons that we see at the spacecraft are a perfect imprint of what the value of this potential is. We also list here the ion and electron temperatures, which govern what that potential is. So this sets up a perfect comparison for the model, because we have the known inputs, what the ion and electron temperatures and densities are, and we can look at the known outputs, and we can use that to compare to these particle and cell models that I've put together. What we see here is just such a comparison. On the top plot, I've taken the ratio of upgoing flux to downgoing flux. So warmer colors are where more flux is coming from the moon in electrons. You see that bright red beam is a nice tracer of the potential. Everything that's darker are electrons that have been absorbed at the lunar surface. And the two lines are model predictions, where we put in the measured electron and ion temperature from the spacecraft, and we're able to produce what our prediction from the model would be for that energy. You see there's two lines. The red does not account for ion temperature, whereas the black does, where we fine-tune the model a little bit. And there's wonderful agreement, meaning that these types of potentials, where the lunar surface is in daylight, it's charged positive, but it's at a negative potential with respect to the plasma, really do exist. And what's remarkable is really that this took up the entire lunar day side. This is a global effect on the day side of the moon. It's not limited to small localized regions. You're really seeing these potentials build up across the entire lunar surface. Moving on slightly, we zoomed in on another series of simulations to look at how very simple shapes in the lunar topography can affect surface charging. This is from a three-dimensional particle and cell code, where we see potential contours represented as color. And the arrow on the side denotes a progression through the day, where the sun and the solar wind are slowly changing angles. And you can see a lot of activity change around the corner of these craters, where it's slowly becoming into shadow from the sun. And the blue colors represent negative potential and negative charge on the lunar surface. And even a very simple shape like this as a crater can lead to enhanced electric fields up here at the edges. I'm showing one example from 45 degrees, so about mid-afternoon. And you can see the electric field magnitude here peaks right at the corner where you're going from a sunlit portion into a shadowed portion. So these types of simulations are really enabling us to get at a lot more of the specifics of how even relatively simple shapes are changing the charge on the lunar surface throughout the day. There's even more recent work on extreme charging. This has been led by Bill Farrell and the DREAM team. He looked at how the solar wind, or the changes in the solar wind from a CME and a solar flare event might change the electric potential. I show another series of curves, mainly just to illustrate that at different periods in this CME, where you have either hotter or colder or more or less dense plasma, can change the entire potential on the day side of the moon dramatically. And that really is simply a driver of what the external conditions are. There's even such an extreme case you see here on the bottom, where the solar wind in the CME was so incredibly dense it drove the entire lunar surface negative, even though it was on the day side. Now, I wanted to point out some implications of this in some future work and try and make some connections about other places in the solar system where this might occur. One recent measurement that we've been looking at is still at the moon, but is of lunar pickup ions. I show here a plate of the lunar sodium exosphere taken in the optical by Jody Wilson et al. In 2006. These neutrals are constantly floating around the moon, and some fraction of them are ionized. It turns out that once they're photoionized, they can be picked up by ARTEMIS. I show an example of these here. And these have very distinct what we call energy and pitch angular spectra, how they're moving with respect to the magnetic field lines. And what we're finding is that when interpreting these photo pickup ion measurements, we have to look beyond the classical picture of pickup ion motion and really look at how the sheath, the surface charging electric field, is actually reflecting some of these pickup ions and scattering them into the ARTEMIS trajectory as it crosses the day side of the moon. So the surface charging really plays a role also in interpreting our measurements of pickup ions. We also look at how surface charging operates in solar wind magnetic anomaly environments. There's been a lot of recent work that's looked at how electrostatic fields govern the reflection of the solar wind. And that's what I might call high-altitude electrostatics. But there's a whole open question of what I might call low-altitude electrostatics, where when the surface actually comes into play in these shielded regions, our photoelectrons are really beginning to dominate even more than usual. And I think this is a really rich area of research for some complex electrostatic and magnetic fields on the lunar surface that's just waiting to be dug into. Finally, a very exciting observation that came out of the Cassini mission around one of the icy moons. Rhea, so there's a polar flyby over the north pole of Rhea. This was reported recently by Santolic et al. In 2011. And these series of plots showed the plasma moment very similar to what I showed from ARTEMIS, where you have nice and undisturbed downgoing plasma to the lunar surface, but coming back up from it is this bite out in high energy electrons, and superimposed on top of that is a nice photoelectron beam. So the exact same processes are occurring at the outer solar system moons as evidenced by this example at Rhea, and I've begun working with the Cassini folks to look into fitting this and making sure that we can understand the same type of process at the outer solar system moons. And this is certainly just one example of many. So wrapping up in conclusion, really in the last few years we've seen a lot of developments in modeling and in spacecraft observations that have really added a lot of subtlety and a lot of richness to our understanding of lunar surface charging. And it's important to note that it's not just a simple plasma physics phenomenon for theorists to scratch out. It has a lot of important implications to other physical processes, one of which is pickup ion dynamics, getting at lunar neutral densities around the moon. Also this supercharging effect, how is it that perhaps or maybe not dust is being levitated in these electric fields, and also, as I hinted at a little bit, any feedback within magnetic anomaly environments. Finally, a lot of the discovery and the understanding that we've had at the moon has implications for many other bodies in the solar system. And really, there's just much more data analysis from ARTEMIS and modeling to dig into to further explore these subtleties. So, thank you.
Thanks, Andrew. Let's take time for perhaps one question. Are there any questions for Andrew? No? Clive.
Andrew, does your work have any implications for how these asteroids and rubble tiles are actually held together? Very small ones. Is that taking it a bit too far?
I would think so, yes. Perhaps, when you crank down gravity, the electrostatic forces begin to grow, especially as a function of grain size. On the moon, some of the simulations indicate that these electric fields are only effective at nanometer-sized grains and smaller, which is important for some context, but for global rearrangement is difficult. Certainly when you get down to bodies that are smaller, Eros and Itokawa, much smaller bodies, it does begin to play a bit more of a role. There's work that Christine Hartzell's done on looking at the scaling to smaller bodies and this dust levitation. But I would be a little careful in extrapolating it much more to global rearrangements. That's I think, more in the purview of bombardment at some point.
Great, thanks, Andrew.
Thank you.
One thing I want to point out is that we at NLSI are very proud of Andrew. He is perhaps, I believe, either the first or one of the first doctorates who's graduated with NLSI support. So with that, I'd like to kind of give him an extra hand. Thanks so much. Our next and final speaker of this session is Tobin Munsat of the University of Colorado, who's going to be talking about recent science results from the CCLDAS Dust Accelerator. Tobin.
Thank you. All right, so these arrows control it. All right, thank you. I want to just begin by acknowledging that this work is really the product of a large team of people as part of the CCLDAS, the Colorado Center for Lunar Dust and Atmospheric Studies, including a number of principals who are in the audience and who've been speaking this week, some staff physicists and postdocs, a small army of students, both graduate and undergraduate, and of course we're part of the NASA Lunar Science Institute, one of the Colorado teams. To begin with, I just want to say that we have a dust accelerator, so that should be the premise for a lot of the scientific studies that I'm going to be discussing in the next few minutes. This is a picture from the corner of the room. You can see the dust accelerator and the beam line and the target chamber. You can tune in at any time you want by going to the internet, dustcam.colorado.edu, and see us working. There are experiments going on, I think, right now, certainly all this week. I should also point out that this accelerator is the beneficiary of a long heritage of this kind of development from our sister laboratory in Heidelberg, Germany, and we certainly trade a lot of ideas, and even people with that lab were very close collaborators with those guys. Just a short technical description before I go into the studies. The accelerator is based on a 3 megavolt electrostatic generator. It's a Pelletron type, which is kind of similar to a Van de Graaff generator. The velocities that we achieve in the facility are tens of kilometers per second, 10, 20. We've designed up to 100 kilometers per second. I'll show you a distribution in a moment. We use active selection of particles so that we can select specific particle ranges in terms of charge and velocity to be admitted to the target chamber. The materials that we can launch are typically conducting materials. We charge them up and then send them through a potential drop to accelerate them. Our workhorse material is iron, but we can launch a whole number of materials. And the sizes that we're talking about are on the order of a micron. The parameters in a little bit more detail. This is a surface plot of the distribution of particle velocities and masses. This is just a little bit more detail on what I was saying before, that the particle sizes are in the micron range, the velocities are in the tens of kilometers per second range. The highest velocity that we've achieved so far is 57 kilometers per second, but each month that we run, we've been up and running for about a year and a half. Each month that we run, we set a new record approaching our goal of 100, or even more as our detection capability gets better and better. The charging and launching process of the particles is a little bit imprecise. What comes out of the dust source and gets launched is a wide range of masses and charges and velocities. So we use active particle-by-particle down selection so that the user can dial in whatever parameters they want and have that arrive at the target chamber. What you're seeing on this plot is a series of signals from detectors at various points in the beamline, which show a single particle entering one detector, going through a second detector. We open up an electrostatic gate to allow that particle to make it to the target chamber, and then we have a final detection to verify what kind of particle we let through. Whenever one has a facility like this, the key parameters are the focusing and the steering and the fluence. We launch on the order of few tens of hertz, a few tens of particles per second, so these are individual particles which come down. We've actually recently developed a dust beam profiler. So if one has a laser beam, it's pretty easy to see where the beam is and how to focus it. You just stick an index card in front of it if it's not too powerful a laser. With a dust beam, it's much harder. So what we've done is we've adapted actually an in-flight instrument called the dust trajectory sensor. We've made a miniature version of it so that we can do real-time monitoring of where every single particle is going through the beam, steer it around with a tiny fraction of a millimeter precision. This was actually put together by one of our students. The performance enhancements of the facility have allowed us to really move on to the research phase, which is what I'm really here to talk about. And we're trying to look at a very comprehensive view of micrometeorite impact processes. And so this includes effects such as secondary ejecta, which are launched, neutral gas, which is produced at impact sites, plasma, which is produced at impact sites. All of those together have a certain energy partition, a division of the energy which goes into the individual processes. We assess this by looking at a number of different experiments, such as light flash experiments, looking at the light that's emitted from the impact site during the impact. We perform those experiments with photomultiplier tube sets so we can get very fast responses. We can look at the angular distribution, look at the spectral content by using filters. I'll show you a slide in a minute about that. We also look at the neutral gas production by using miniature Bayard Alpert ion gauges. We also look at do a kind of a post-mortem on the impact sites to look at the evidence of the cratering and any residue that's there and the shapes of the craters. And then all of this goes into our fundamental understanding, which can lead us to better instrument development and, of course, even calibrate instruments that are developed. So just to give you a kind of a sampler of the type of work that we've been doing, one of the experiments has been temperature measurements of the impact plasma. These are very brief and very small impact plasma production. We measure the black body temperature and the radiated power using photomultiplier tubes. And I'm just going to fly to the next slide and show you that we can actually resolve in time. If you look, this is actually time-resolved temperature measurements and time-resolved expansion area and time-resolved radiative power. And on the right side, we can actually look at the two individual dust impacts and look at the temperature decay over time. And in the middle there is a dotted line, which is a model, which is using an estimate of what the temperature decay should be based on radiative decay with a certain fraction of the impact or mass going into the plasma. We can also detect very, very tiny amounts of neutral gas emitted from individual impacts. What we're looking at here on the top is one of our mini ion gauge signals during a single impact. And just in order to make sure that we weren't having just a noise signal, we turned off the collector and turned off the filament and got a very sharp peak, which is a noise peak, but that's very different than the actual signal peak, which indicates the neutral gas which is collected. And the resolution that we're looking at is something like a pressure rise locally of a few times 10 to the minus 10 torr in the middle of this detector. So this is actually very valuable as part of this comprehensive picture of the impact process. We also look at secondary ejecta. Of course, when micrometeorites hit the surface, they eject particulate matter, which can over time lead to the production of rings around moons or dusty atmospheres or dusty exospheres. And so we monitor this using filtered photomultiplier tubes. What we can do is actually look at the initial impact flash as the particle comes down the beam and impacts a target, and then any secondaries that come off will actually impact the face of the photomultiplier tube, and that can be used as a time-separated second signal to measure the characteristics of the secondaries and also the relative timing. And so this is just a quick image of one of the plots of the data that we got from some of these primary and secondary flash experiments, where we can fit an exponential to the primary flash and separate it out and detect with very, very high fidelity the secondary flashes on the photomultiplier tubes. We also do post-mortem on the cratering. This is done by one of our grad students, Anthony Hsu. And so this particular image that you're looking at is a crater from PVDF, which is a material that is used in dust detectors, for example, the student dust counter, which is in flight right now. This material has a permanent polarization in a dielectric, when the particle comes in and creates a crater, that creates it removes some material, creates a change to the polarization, and that little blip of charge can be measured on a detector to analyze what kind of impact. Of course, to figure out what those signals mean, the instrument has to be calibrated, and in order to calibrate the instrument, one has to connect the launched particles to the crater size to the signals, and all this is done in our laboratory. Right here we can see an electron micrograph or electron microscope image of the crater with you can see the spatial bar down there, 1 micron. So this is a very, very tiny crater which is imaged with high fidelity. And we can tilt the image and use what I'm showing here is sort of a nice looking movie, but we can actually use this to do stereoscopic reconstruction of the depth profile of the cratering. So we can actually compare the stereoscopic reconstruction with an actual cutaway using a focused ion beam. And so we can calibrate our stereoscopic reconstruction and run through an enormous number of craters to develop calibration settings or develop the relationship between the impactor size and the crater characteristics. We also do mass spectroscopy. This is just an image of a linear time-of-flight mass spectrometer, which I'm going to just skip through in the interest of time. This is a picture of the instrument in our Accelerator target chamber. And this is just a picture of what one of the spectrum looks like with iron impacting an instrument witness plate, which is made out of primarily silver and rhodium. So if you look closely on this image, you can see the silver lines, you can see the rhodium lines, and there are also a number of contamination lines. Identifying a library of these types of spectra based on the impactor characteristics, the target characteristics, and the impact characteristics, of course, allows us to have a reference library for putting instruments up into flight and interpreting what that data means. And of course, we're doing this year by year by year. Sasha Kempf and our group has been doing this for many years. In addition to the spectrometer, the mass spectrometry tests, we actually are doing tests on very basic dust detectors, which may be accidental dust detectors. The stereo mission has antennas that they are getting somewhat anomalous signals on that they think may be dust impacts. So we've actually done a mock-up of this. Professor Zoltan Stranovsky in our group has done a mock-up of this, and sure enough has found similar kinds of signals on a very simple mock-up of this kind of antenna. And the next stage of this development is to build a better mock-up of what the real stereo antenna looks like, as well as putting together witness plates for impacts which can be used in conjunction with the antenna electrical signals to correlate dust impacts. So this is a proof of principle witness plate which is proposed to go on solar probe. And lastly, I just want to point out, I think most of the people in this room know about the lunar dust experiment. This is maybe the highest profile instrument which is being calibrated in our laboratory because it's launching very soon. And so here's just an image of the LDEX dust instrument, which is going up on LADI, being calibrated in our facility. And I just want to close with a very simple point, which is that when we started this project, one of our charges from the NLSI was to be a facility and to be a resource for the larger lunar science community and the larger space science community. And so I hope that people just have a takeaway that this is a very unique facility. It's a very unique little corner of parameter space, at least on Earth. Out in the cosmos, it's a very common area of parameter space. But we have this facility right here in the U.S., and so I hope that people come and take advantage of it. Thank you.
Very nice. Thank you so much, Tobin. Let's take maybe one question for Tobin. Anybody have a question here? I know we're running a little bit over time. No questions? Okay, great. Well, then I would like to thank all of our speakers in this session and the AGU for making this an on-demand session, and especially our organizers for this event all day today. Was put together primarily by Brad Bailey and Mihai Harani, and David Morrison and I helped just a wee bit. But thank you to all the speakers and to the organizers for doing it, and thank you again to Tobin. So with that, I will close this out, but let's thank everyone one more time.